In this video, we want to look at Kirchhoff's voltage law. This law states that in a closed circuit, the voltage around that circuit must add up to zero. Now we need to understand that in a resistor, current flows from area of higher potential to the lower potential, maybe let's say minus 8 volts. But we need to understand that when energy flows in a resistor, that resistor decreases the energy of the charges. Because of that, we assign negative V to it, negative voltage, because it reduces the energy per unit charge. As for a battery, on the other hand, a battery current flows in it from low potential, area of low potential, to area of high potential. So from here it goes this way. But sometimes if it flows in a reverse direction, let's say it flows from this, then if it flows in this direction, then we know that the charges are depleted. So because of that, we assign negative voltage to it. This question says, what is the current that flows through the circuit? That's this circuit. Second one says, determine the voltage and voltage drop at points A, B, C, and D and show that the sum of the voltages add up to zero. Now, looking carefully at this circuit, we'll notice that only one battery source is here. So the first thing we're going to do is to first of all determine the direction of this current. And when we look at this, we notice that it flows from area of higher potential to area of lower potential. So the current will flow this way, through this direction. That's what the direction of the current. So the voltage of the battery, 10 volts, is what is powering this circuit. And so what we're going to do is to sum the voltage of the battery. The resistance is going to reduce or cause a voltage drop, is going to consume energy. So minus V, let's call it V1. This is also going to reduce energy, we call it minus V2. This is also going to reduce energy, we call it minus V3, and they will sum up to zero. Now, if we turn V, according to Ohm's law, is equal to IR. So we can say negative IR1, negative IR2, negative IR3, and it is equal to 0. So 10 negative, we don't know the value of I, but we know the value of R1, and R1 is 6 ohm. So it's going to be 6 times I, 6I. We don't know the value of I, but we know the value of R2, 8 ohm. So we're going to have negative 8I2. We don't know the value of I, but we know the value of this 10. So 10I3 is equal to, sorry, R 10I only, 10I equals 0. So the next thing now is to 10 V minus, since I is common, we're going to evaluate and say I into, we have 6 plus 8 plus 10. This minus affects all of them, and it is equal to 0. So we have 10V minus, if we add all of this, we're going to get 24. So 24 times negative I is 24I here. So it is equal to 0. So if we make I subject of the formula, it will be 10 volts divided by 24, which will give us about 0.24 approximately. Sorry, 0.42 approximately. Remember, when you approximate, it's going to affect your final answer. It's going to affect your final answer, because when you approximate, you lose some values. I know they may be same is significant, even if though they are insignificant, but it will affect our final answer. So looking at the circuit again, we will notice that the electric potential at A is 10 because it has not encountered any encumbrance, any resistance. So the value at that A is 10 volts. So at point A, it is 10 volts. But at point B, we know that V is equal to IR. So what we're going to do is the value of V can be gotten by I. Our I is already 0.42 times the R that is there is 6 ohms. So if we multiply that, we'll get 2.52. So this is the voltage drop that is there. Therefore, for us to get the one that is at point B, it will be that 10 that is coming, minus 2.52, which will give us 7.48 volts. So this will be the voltage at this point B, 7.48 volts. If we want to show all working here, we'll just say change in voltage is equal to negative IR1, so that we can say that VA, this will be VB minus VA, which is, if we make, is equal to negative IR. If we make VB subject of the formula, VA will come over here and becomes positive, so VA minus IR, which is, our VA is 10 minus 0.42 times 6, because this is R1, so which gives us 7.48 volts. So using the same pattern, change in V at point C. So change in this is equal to negative IR2. Now IR2 is what we're going to use. So VC minus VB, because we're looking at is this. So VC is now equal to VB minus IR2. So our VB is already 7.48 minus our I is 0.42 times our R2 is 8. So the value we'll get is around 4.12 volts. So that's, so for us to get the potential drop that is across R03, remember V as usual is equal to IR. So our I is 0.42 times our R03 this time around is 10, so which will give us 4.2. And if we now check at that point, which is 4.12 minus 4.2 will give you about 0.08 something, because of the approximation that we did initially, I told you. So our answer is approximately 0. This other question now says, show the sum of the voltage drop in the circuit, show that it equals 0. Now if you look at this circuit, you notice that there are two batteries. Now this will flow through this direction and this will flow through this direction. So because of that, both of them are going clockwise, so they support each other. So since they support each other, the current will flow in the same direction. So if we call this battery 1 and call this battery 2, so since this is moving this way, it's going to be positive V. So let's call it battery 1. So positive minus, this will cause a voltage drop, so we call them negative V1. This is going to increase it, so positive V battery 2, and this is going to cause a voltage drop, so negative V2, and all of them equals 0. So let's just solve at the side. So because of that, the positive, the first one is 10, let's say 10. This is negative 40, because negative 40 and V is equal to IR, so 40 times I, 40 times this R, 40 times I is 40I, 40I, and VB2, that is 6 volts plus 6 volts. This IR, so 20 times I will give you negative 20I equals 0. So the next thing we do is to collect like terms from here. So this and this will give us 16. So we say 16. This and this is going to give us minus 60. I equals 0. So minus 60I is equal to, this coming over becomes negative 16. Negative cancels negative. So 60I equals 16. So I equals 16 over 60, which will give us 0.1 ampere. So for us to now get the voltage drop in V1, it is equal to IR1. So our current is 0.1 times the resistance there is 40, which will give us 4 volts. Therefore, the voltage that is 10, that is coming out 10 minus the voltage drop, gives us 6 volts. So the potential that is at C is going to give us 6, because at that B point, nothing has dropped. Nothing has dropped. So the potential at C, or if we want to show it, we can say change in V is equal to negative IR1. And remember, this is VC minus VB, which is equal to negative IR1. And if we say VC is now equal to, this becomes positive minus IR1. So the voltage drop at C gives us VB, which is 10, minus I is 0.1 times 40. And if we resolve that, we're going to get that here is already 4. So 10 minus 4, 6 volts. The next one is for us to get VD. VD minus VC. The potential drop at D, point D, junction D, minus that of C is equal to, since there is a battery at that D, junction D, the battery is going to add a lift to that junction. So it's going to be positive battery, is going to be positive VB2, battery 2. So VD is equal to VC plus the battery 2 is 6 volts. So we have that VD is equal to, here we have 4, and the difference of that 6, which gives us 2 volts. So for VA, for us to get it, is VA minus VD is equal to negative IR, because there's a resistor there that is going to bring down, so bring down the voltage. So we have VA is equal to VD minus IR2, so that VA is equal to, here we have 2 already, we have 0.1 times R2 is 20, so we have 2 minus here is 20, 2 minus 2, which gives us 0. So